Lesson 2.1 over composition of functions. We are going to be evaluating the composite at a given value of x, find the composition of one function with another, find the composition of functions from graphs and tables, and use combinations and compositions of functions to model and solve real-life problems. So as we move down here to the definition of composition of functions, here's how it reads. The composition of the function f with the function g is, and they gave us some notation here that are equivalent to each other. We're going to talk about how that is read. The domain of f composition g is the set of all x in the domain of g such that g of x is in the domain of f. So as far as how does this symbolic notation read, okay, the first one there, the one with the little inner circle, open circle, you read it as, and I'm going to put little quotes here, f is a composition of g of x, okay? Now the equivalent to this left-hand side is the functional notation on the right, which is what you are more accustomed to seeing, is read as f of, sorry about that. Why is it doing that? G of x. Okay, so both of these expressions are equivalent to one another. Composition, in essence, is glorified substitution, okay? So what instead you are doing is, instead of just evaluating a function at a particular value, you are instead going to be substituting expressions, as seen as the example number 1 that we're proceeding to look at. So I'm going to give you two examples. One is f and one is g. F is x plus 2 and g of x is 4 minus x squared. And we're going to find the composition of these functions in both directions. So first, f is composed, find the f composition of g of x. So let's rewrite it into what you are more familiar of being accustomed to seeing. Let's do function notation. So f of g of x is equivalent to f of composed in g of x. Notice that the lettering and all that does not change the order, right? The f, the g, then the x, you're just writing them with parentheses. Now, as you guys learned in previous unit, we will always start with the innermost section of our parentheses. The g of x, we are going to substitute what g of x is, and if you look upstairs, g of x is 4 minus x squared. So we're going to bring down this equal sign, bring down the f, and we are going to replace g of x with 4 minus x to the second power. Okay? So what does this notation say to do? Well, what it says to do in pure simple words, and I'm going to write it over here to the right so that as you do these problems, you too can verbalize it to yourself. Look at the function f and substitute every x with 4 minus x squared. That's what that notation there means. So let's look at the function f. Here's our function f. All right, they want us to replace every single one of the x's that we see in that function after the equal sign, okay? The definition, f of x, that's just the name of the function. Every x needs to be replaced with 4 minus x squared. The only x that we need to replace is this one right here. That's the only x. So let's rewrite the function f of x with this new notation. So I'm going to put an equal sign here more to the left to give me space. Replace that circle value with 4 minus x squared, because I'm replacing the x with the new function 4 minus x squared, and then the plus 2 just merely will come down. I'm going to combine like terms. The 4 and the positive 2 makes a 6. So negative x squared plus 6 is my function answer, or you could have also written it as 6 minus x squared. Whichever one of those is acceptable. Okay, so all we merely did was substitute, replace that x with the composed function. So let's go and do it in the other direction. Let's go ahead and choose a different color here. Let's rewrite g composition f of x as g of f of x. So again, I am going to replace the inside function with the definition of f of x. So let me erase this over here. So the definition of f of x is x plus 2, right? So let's rewrite, bring down the g function, and for f of x, I'm replacing it with x plus 2. So now, instead of what we wrote in black for the left-hand side, we're going to say, look at the function of g and substitute every x with x plus 2. So I'm going to look at the function g, and I'm going to replace every x that I see, which in this case there's only one, with x plus 2. So let's do that. So after the equal sign, there's a 4, there's a minus, there's that x I need to replace. I'm replacing it with x plus 2. I'm going to put a parentheses around it because that entire quantity has to be squared. Now I'm going to do some simplifying. So the 4 comes down and the minus comes down. X plus 2 raised to the second power is x plus 2 times x plus 2. I am now going to distribute so that I can expand that multiplication. I'm going to put open parentheses because that minus is going to have to be distributed after, right? So I need to multiply x times x, x times 2, 2 times x, and then 2 times 2. And when I do all that, I get x squared plus 2x plus 2x plus 4. And these here combine to 4x, right? So once I distribute that negative 4, the minus x squared, the minus times 4x becomes minus 4x, and the minus times the 4 becomes a minus 4. I will notice that this 4 and this negative 4 is going to zero out. So the final answer for this problem is negative x squared minus 4x. Okay, so what I'd like you to do now is challenge yourself with doing x minus 10 as being the function of f of x, g of x being the function x squared plus 2x minus 7, and you are going to find the composition g of f of x. All right, so again, take g composition f of x and go ahead and start off with this notation and move forward. So pause the video now and get working on that, and when you are ready, go ahead and unpause and check your work. See you in a bit. Okay, welcome back. Here's example 2. The final answer was x squared minus 18x plus 3. So let's talk about this just in case you need to. So what does this expression say to do? Well, it says to look at the g function, and wherever you see an x, you need to replace it with x minus 10. So there was an x right here. There was an x right here. So those needed to be replaced by x minus 10. So that's what I did right here. So instead of x squared, it was x minus 10 squared. Instead of 2 times x, it was 2 times x minus 10. And then the 7 just came down. And from there onward, all you're doing is algebra. That's all you're doing. You're just simplifying. So I rewrote x minus 10 squared as x minus 10 times x minus 10. I multiplied. In the next step, I went ahead and distributed. Negative 20 minus 7 becomes negative 27. And then I just combined like terms to be able to get this answer. So this brings us now to example number 3. Example number 3, notice that we're still giving you two functions, one f of x and one of g of x. I usually use f and g, but just know functions can be named with any letter, m of x, g of r, t of s. So anyway, we're just remaining with the consistent f of x and g of x. So we are going to evaluate f composition g of 2. So here's a little slight difference. We still, though, are going to abide by the rule of rewriting it as f of g and instead of x of 2. So notice here, our x is being replaced by the number 2. The x this time is given, whereas in example 1 and 2, we were not given what x was. You are still, mind you, going to start with the innermost value, and that says to substitute x with the number 2 in the g function. So I'm going to go to the g function, and I'm going to say that g of 2 is 2 to the second power, and 2 to the second power is a 4, okay, because I had to replace 2 for every x. So I come back over here and found out that g of 2 was 4, so I get rid of that and replace it with the answer I just got. Now it tells me, hey, look at the f function and replace it with a 4. The x values, replace the x values with a 4. So I'm going to come over here to the far left. I need to evaluate f of 4, which means I need to take my equation, and anytime I see a x, I need to replace it with a 4. 4 plus 4 is the square root of 8, but I can break down square root of 8 as 2 square root of 2. So the final answer to my question is actually 2 square root of 2. Okay? If you are asking yourself, wait, how did she go from square root of 8 to 2 square root of 2? Let me remind you that back in geometry, one skill that teachers taught students was the factor tree. You took the value in the square root and you factored it to prime numbers. So 2 times 4, but 4 can be broken into 2 times 2. You take all your prime factors, right? And you ended up with a 2 times a 2 times a 2 in this particular tree factoring image. All pairs leave the radical, right? The square root of 4 is 2. So when it leaves the radical, it becomes a 2 on the outside. And then the other 2 had no other pair to pair up with to be able to leave the square root. So 2 square root of 2 is your final answer. So go ahead now and do part B on your own, and then come check out your final answer. Okay, here is part B. So we started out with the f function. So we came over here and substituted 7 into the function and got 50. Brought the 50 over here, and now that just means, hey, go to the g function and replace x's with 50. That's what we did here. And when you got square root of 50, you can reduce that radical to 5 square root of 2, and I've given you how we did that. And so 5 square root of 2 is the final answer for this problem. All right, let's try one with absolute value. So I am going to now rewrite this. So f of g of negative 10. So let us take care of that. g of negative 10 tells me to go to my g function and replace x's with negative 10. And in the process of doing so, negative 10 plus 6 is a negative 4. So I bring down my f, and the g negative 10 I just found is the answer, so I put negative 4. Then it says, okay, you're at f, take that x value and go to the, you're at negative 4 on the x-axis, take that value and go to the f function. So I'm going to come over here to the f function and evaluate f of negative 4, which will be the absolute value of negative 4. And the absolute value of negative 4 is merely just a 4. Go ahead and do the next one. Pause this video and check your answers. Okay, welcome back. Here is that last problem. The final answer is 11/4. Some students have been asking, do I accept decimal values? I do, but I do need you, please, if you are not comfortable with fractions, you need most definitely to find that practice, because we will be dealing with fractions a lot in coming units. Okay? All right, let's move on here to example number 4, tables. I won't do every single one of these, as I want you as well to partake in obtaining these answers. So let's just do part A and B. All right, so part A and part B require us to rewrite that composition. So I'm going to do that first. So f of g of 1. And the other one is going to be f of g of 2. Okay, so here's how you read this table. I do want you to realize that this table has 3 rows. The first row is my x row domain, and then it gives me the output values, the range values for 2 functions, x with respect to f of x and g then with respect to g of x, okay? So the first thing we do is we start from the innermost valley. It's asking us to look at the x value 1 and go to g. Look at x equals 1 and go to g. So let's do that. I'm looking at x equals 1, and I'm going to go to the g function. And what do I see? The g function has a 0. So I'm going to put f of 0 for the yellow highlighted g of 1. Okay? Notice I'm going to erase. I erased. Let me go ahead and erase these lines for a second. And now I'm asked to evaluate f of 0. So that means I need to start at 0 and go to the f function, which in this case is a 5. So I'll put 5 right here, and that is my final answer. Let's try it again. We are starting with g of 2, where your x is 2. So I'm going to start here at 2, and I'm going to go to my g function, which is 2 rows down, okay, because it says here, go to your g function, right? So g function is going to be 3. So let's replace that with a 3. So I'm going to cross through g of 2, and I'm going to say f of 3. Now, it says to go back to your x value of 3, and look at f. And in this case, it's a negative 1. So I would like you to take a moment and figure out the next 4 on your own. Okay, we're back. Check your answers. You can pause the video at this time just to make sure you got them all right. Make sure you understand. Okay, so now that you've mastered how to use tables to determine the values of composite functions, let's have you do graphs. Now, you did this a little bit in Unit 1, so this might come a little bit easier for sure as far as graphing the technique. The only difference is in Unit 1 we use several graphs, and here we're putting several graphs on one plane, but it's the same approach. So what I want you to do is go ahead and rewrite the composition format into function notation format for all of them. So pause your video and go ahead and do that, and then we'll get started on evaluating those functions. So pause now. Okay, so this is what yours should look like. I'm just going to do the first one. You will be responsible for doing the next 4. Okay, so we are going to make sure you understand one thing here, and that is your x-axis is going to be the focal point of where you start every single problem, okay? You must start with your x-axis. So I purposely highlighted it here because I want you to understand that your values, they're giving you x, okay? And they're wanting you to start on the x-axis. So the x here, let me point here, this here, these values are your x values. That's the starting value. So I am standing right here at 3 on the x-axis because this is my x-axis. And I'm starting here at 3, okay? Now they're telling me the 3 has to go to my f function. What you need to realize is that you have 3 functions here, all right? So if I'm starting here at 3 and I need to go to the f function, which is right here, where do I need to go? Well, if I'm standing here, I'm going to go 1, 2, 3, 4 units down to touch that f function. So h comes over, open parentheses, I had to go down 4 to get to the f function. So I'm evaluating f of 3, okay? That's what I just finished doing. Now it's asking me, hey, start over. Start at the -4. So the -4 is right here, okay? That's where I'm standing. I'm standing here at -4 and it's telling me to go to the h function. Well, where's my h function? My h function is there. So from this -4, I'm going to go 1, 2, 3, 4, 5 units up to touch the red graph of my h function. So the answer to this is 5. And this is what you would type as a final answer. So go ahead and attempt to do the next 4. Pause the video and then check your work. Okay, take a look at your answers. -3, -6, 2, and 0 should have been your answers for these last 4 problems. Okay, so let's jump into this last problem, example number 6, application of composition of functions. So let's see how composition can be used to model and solve real-life problems. Here goes. The number n of bacteria in a refrigerated food is given by n of t equals 20t squared minus 80t plus 500. The t value has to fall between 2 and 14. And t is the temperature of the food in degrees Celsius. Okay? T is the temperature of food in degrees Celsius. Now, when the food is removed from refrigeration, the temperature of the food is given by T of t equals 4t plus 2, where the little t has to fall between the range of 0 and 3. This time, the t stands for the time in hours. Okay? So, they want us to compose n composition of t of t. So, let's rewrite that. So, instead of n composition t of t, let's write it in function notation, n of t of little t. Okay? Again, we do what we've been doing. Just because it's an application problem, the approach is not going to change. We are going to take care of inside first substitution. Replace capital T of t. So, equals n, open parentheses, replace that green with 4t plus 2. So now what does that notation mean? Again, like we did in one of the first page, we are going to look at the n formula, right? And what are we going to do? We are going to substitute each capital T with 4t plus 2. Okay, so if you learn how to read that notation in this layman terms type expression, you will understand what you need to proceed doing. So let's do what the direction says. Look at the n formula. Where's my n formula? Right up here. What do I need to do? I need to replace every capital T. So every capital T, that's a capital T, that's a capital T. With what? With 4t plus 2. So let's do that. So 20, open parentheses, replace it with 4t plus 2 squared, minus 80, replace it with 4t plus 2, and then plus 500. So that's the composition of n composition T of t. Okay? So that is the number of bacteria with respect to time. Number of bacteria with respect to time. Let me write that down. Number of bacteria, okay, after time t, with respect to time t. Okay. So now they're asking you in part B, find the time, which is T, right? Find the time, which is T, when the bacteria count reaches 2,000. So the bacteria count is the number, right? So find the time when the bacteria count reaches 2,000. So our formula, this formula that we just came to do here, this is n of t right here. Let me just write this down like this, right? This formula is what we're supposed to use to find T. They're telling us that the number of bacteria is 2,000, so I'm going to substitute n with 2,000. And I'm going to set it equals to the formula, and I have to solve for T. But we're going to use a graphing Desmos calculator approach to solve for T. So these two sides, I'm going to put this in one equation and this in another equation. All right? So let's go to Desmos. So right over here, I've already typed it out. Okay? The first formula, the only difference is I changed the t's to x's. Okay? So I typed the n formula and then I put y equals 200. But you'll see that we don't see the graphs at all. So I'm going to come over here and I am going to change my y values to some bigger numbers. Let me pause here a second. Let me adjust those numbers so that we can see the graph. Let me see if I can actually just squeeze it here and make it faster. Because the numbers are going to get really big. There we go. And then let me stretch it. So there we go. I guess this is faster. So as I maneuver here, give me a second. This is probably going to take too long. Let me pause and let me adjust it using these right here. Okay, here we go. So I adjusted the x-axis to somewhere like, let me put this better, at -2, which is your time, to 8 seconds. So -2 to 8. And then the y-axis, I went from +15 to 3,000. So if you look here, here's our graph. And the graph is intersecting right here and is intersecting right here, right? We don't want this one because our time is not going to be -2.22. We don't go backwards in time. We're going to use the 2.22, and it intersected at 2,000 as far as the number of bacteria goes with the black line, the horizontal line. So our T value approximation here is going to be, T is going to be around 2.22 hours it takes for the bacteria to grow to 2,000.